Vector function, okay? It's a function, simply the definition is whose values are vectors, okay? It's a function anyway. And that depends on P, the point in space, okay? So we could write this. V vector is function of P, and each component of the vector is function of P. So it's a P, okay? There's a point in space. Okay. And if it's a Cartesian means what? IJK, okay? X, Y, Z. This space is called Cartesian. All right? And if it's a Cartesian, this is arbitrary space, okay? It doesn't have to be any coordinate, but if it's a Cartesian, you could write that like that, right? It's the coordinates of X, Y, and Z. So it's a function of X, Y, Z in Cartesian, okay? That's a vector function. Scalar function, that's a function whose values are scalars. That depends on, location of P. And this is the, what? This is the function that we used to do, right? And this is a vector function. 자, 스케일러 펑션 우리가 늘 봐오던 그 펑션이죠, 그렇죠? 근데 벡터하고의 상관관계로 스케일러라는 말을 붙여서 쓰는 것뿐이에요. 이거는 우리가 늘 보던 펑션이고, 이거는 벡터 펑션이죠. Okay? So those two functions, vector function and scalar function, makes field. Okay? So we have vector field and scalar field. Vector fields are, vector function defines the field. Okay? Like this. This is a surface, for example, and this is normal vectors. Okay? The normal is different from each location, right? Each location, that should be different direction. Right? So we could say this is a normal vector field on that surface. Okay? That's the field. And scalar field, this is normal graph, right? X, Y, Z. There's no direction, but on each, point in the space, they have unique values. Not unique, but some values, right? And that's a scalar field. So all the function, 2D or 3D graph is really scalar field. Okay? Like temperature field in a body, pressure distribution, on a system, that's all scalar field. Okay, let's take an example. Example 2. On page 377. So it's velocity field. Okay? So let's assume that we have a disk. Disk is what? Rotating disk. We have a thin layer of circle. This is a thin disk. Okay? And this is solid disk. And it is rotating around z-axis like that. So counterclockwise. Counterclockwise. Okay? It is rotating that way. Then the translational velocity. This is rotational velocity, right? This let's say this is x. No, sorry, this is y. And this is x. And this is c. Okay? So we have two velocities there, right? When the body is rotating. So we have rotational velocity here. That's w. Okay? And it is rotating to z direction. That's what we define. And we need to get translational velocity on any point in the disk. Okay? So here, if you have a velocity there, this is, this is rotating that. So translational velocity is tangent to the rotation, right? So it should look like that, the velocity, okay? And if it's outer, side, it is, faster than inner side, right? So that it rotates together, right? So from here, it's to the backwards, and this part will be faster than the other part, right? And this part, like that, and that part faster, same thing here, and faster, okay? So this is the distribution of the velocity around the, disk, okay? That's field. Those are field. Velocity field, okay? The collection of all the, vector changes, that's velocity. Okay, so from the physics, we know that the translation of velocity is different from the position, at different positions, right? So that's cross R. R is a position vectors, okay? It's R. To that point, okay? So it's a R cross, omega cross R. That's the, velocity, the direction, okay? So if you do that, the direction is tangential to that, right? It's to that point. So how can I draw that? So let's say this is W, and this point, this is R, okay? That's 90 degree here, right? If that's the case, then the direction is this right-hand screw rule, right? So from here to here, rotating, so it's that. Yeah, right? So it's like that, right? So tangential to that plane. So that one really, represent that things, okay? So V vector is I, J, K, and the rotational velocity has component on z-axis only, right? Because it is rotating around z-axis. That's what it is. And R is x, y, z, right? The position vector changes. Okay, so that's minus y minus wy wx and 0. Okay, so now we understand what the vector functions are, and we are ready to define the derivative of that function, right? Since it's a function, we can find derivatives. Okay, this is quite usual definition, right, for the differential of with the variable t. Okay, so that's without the proof. We just take it, right? So each component. So the derivative of a vector is the derivative of each component. Okay, and that's the usual properties. You could put a constant value in anywhere, and this is derivative distribution, right? This is distribution of inner product, and this is the distribution of cross product. This is the distribution of triple product. Okay? We just take it, without proof for this. And since the total derivative has defined, we would be able to define the partial derivative of a vector function that is function of t. V is function of t1, tn. Okay? Let's assume that we have an n number of different, variables there for, v, vector v. Okay? And that's component. Each component is a function of n, variables, right? And then out of that, Tm is a arbitrary, an arbitrary variable, right? For example, dv over dt 1001, right? There are infinite number of, n number of variables, and out of that, we just take derivative with respect to just one of them, right? Then that's how you write it. V1 dt 1001. Okay? dv2 dt 1001. That's how you do. That's partial derivative, okay? Other variables other than, 1001 is constant, right? In that respect. Okay, and second, second partial derivative is you're doing another thing, right? So d v over d t 1001, the other is like t over 2002. I don't know, right? That's what you do. Chain rule.